E equals hf is, in my opinion, the most brilliant mathematical equation. But Einstein's more famous for another of his equations, E equals mc squared. In this lesson video, we're going to learn about the significance of that equation and also get an understanding about how it relates to nuclear fission, nuclear fusion, and why those forms of power have got so much potential, and why nuclear weapons can be so devastating. Okay, so first off, let's get the equation right. Delta E equals c squared delta m. Yes, I know I just changed the order, but that's to emphasize something really important. Delta E is the change in energy, delta m is the change in mass, and c is a constant. Is c the speed of light? Well, yes and no. You learned about refraction before, and so you should know that in glass or water, light slows down by 30% or so. So a better question might be, is c the speed of light in a vacuum? Well, yes and no. C has a value of 3.00 times 10 to the 8 meters per second, and electromagnetic radiation travels at a speed of 3.00 times 10 to the 8 meters per second in a vacuum. Maybe it's better to simply realize that C is a constant, and it is a constant with a value of 3.00 times 10 to the 8 meters per second. The value of C does not change in a vacuum, in glass, in water. C is a constant. Sometimes light travels at this speed. So back to the equation, the change in energy is equal to a constant times the change in mass. Delta E is proportional to delta m. And I wrote the equation as delta E equals c squared delta m to emphasize this really important point. Delta E is proportional to delta m. We often describe this as saying energy and mass are equivalent, or mass is a form of energy. So that's what the equation is referring to, but how and where do we use it? Let's look at particle physics. I have 6 protons and 6 neutrons. They're all separate, like ping pong balls on a tray. They're not interacting. Over here on this other tray, I have a carbon nucleus. It also has 6 protons and 6 neutrons. But just thinking about the nucleus, so no electrons or anything like that. So the contents of the 2 trays are exactly the same. 6 protons and 6 neutrons. If I get some scales and place the trays on either side, they will, of course, balance. Except they don't. The tray with the separate particles drops down, showing it has more mass than the nucleus. Now, since these are scales, we can find out how much more mass the separate particles have, and some incredibly sensitive measurements showed that the protons each had a mass of 1.672623 times 10 to the minus 27 kilograms. Neutrons are 1.674929 times 10 to the minus 27 kilograms, whilst the carbon is 19.926483 times 10 to the minus 27 kilograms. So what's the difference? The tray with separate particles has 6 times 1.67623 times 10 to the minus 27 kilograms plus 6 times 1.674929 times 10 to the minus 27 kilograms, giving a total of 20.085312 times 10 to the minus 27 kilograms, compared to 19.926483 times 10 to the minus 27 kilograms for the joined up nucleus. That's a difference of 0.158829 times 10 to the minus 27 kilograms. It's not a lot of mass, but that is a defect, and we call it the mass defect. So the mass defect is a difference in mass between the mass of a nucleus and the sum of the masses of the individual components of the nucleus. Here, the mass defect is 0.158829 times 10 to the minus 27 kilograms, and that is delta M in the equation. Now this is a key finding. The mass of a nucleus is less than the mass of its constituent parts, and the difference, the mass defect, delta M, is the delta M in the equation delta E equals c squared delta M. Where did the mass go? That's easy. Einstein's equation tells us it became energy. Delta E equals c squared delta M. 3.00 times 10 to the 8 squared times 0.158829 times 10 to the minus 27 gives us 1.43 times 10 to the minus 11 joules. That's a very small amount of energy, but when we're doing particle physics, we can have so many particles that the energy that we get in total is huge. This energy is released when the particles join together to form a nucleus. We start with 12 particles separated to infinity with a total mass of m1. They come together, forming bonds and becoming a nucleus, and the total mass drops to m2. This gives a mass defect delta M equals m2 minus m1. Through delta E equals c squared delta M, energy is released. This is called the binding energy. The binding energy is the energy released when the constituent particles bind together to form a nucleus. Going in reverse, the exact same amount of energy, the binding energy, is required to break the nucleus apart into its constituent parts. And that's a good place to stop. We still have some complexities to cover regarding the binding energy, but please make sure you understand this core part of the theory first. The mass of a nucleus is less than the mass of its constituent parts. This difference in the mass, delta M, is called the mass defect, and it is the delta M in the equation delta E equals c squared delta M. And delta E is called the binding energy, and it is the energy released when a nucleus forms, but also it's the energy required to break the nucleus apart.